Section 4.4, Step Functions. We continue to study differential equations. In this chapter, we're using Laplace transforms as our technique for solving differential equations. But in this section, we're going to focus on a specific type of function, namely discontinuous functions. Throughout our calculus careers, we almost exclusively work with continuous functions. So why are we interested in discontinuous functions now? Well, in a lot of contexts that are modeled by differential equations, discontinuous functions can arise naturally. I give one example here. Suppose we're studying a mass spring system. Specifically, imagine the spring is the suspension on your car and the mass is the wheel that it's attached to. In that scenario, it's not hard to imagine something, maybe a pothole or a rock that you drive over, that would instantaneously jolt the system, instantaneously introduce a force which almost as quickly dissipates. How would you mathematically represent such a force? One representation could look something like this. My green function here is 0, and then at some moment it instantaneously jumps up to some non-zero value. It remains non-zero for a very, very brief moment, and then it just returns to 0. This is the type of discontinuous function that we're interested in this section. And this function is not completely foreign to us. We've seen functions like this before, but I think you would admit you don't often work with functions like this in a calculus class. So this is what the graph of such a function could look like. How about the equation or the formula that represents that function? I've noted here that we would use a piecewise function, so that for t values between 0 and c, the function would be 0, and then at t equals c, the function instantaneously takes on a non-zero value. And then some very short interval later, the function goes back to being 0 once again. So we might represent it something like this, with these different cases for the function depending on the different values of t. So since these functions occur regularly in contexts modeled by differential equations, we need to be able to handle them when they arise. In the specific context of our mass spring system, this force, as I've described it, would be an external force acting on our system. It would be the g of t term that makes the differential equation non-homogeneous. So imagine you have such a g of t and you want to implement, say, undetermined coefficients to solve the differential equation. You would need to set up a distinct differential equation for each of the cases that occur in your g of t. Such a process is doable, but it's not particularly efficient. So our goal will be to familiarize ourselves with discontinuous functions. We'll actually introduce a specific representation of such functions. Then derive the Laplace transform of such a function, with the goal that we can use Laplace transforms to solve a differential equation containing one of these discontinuous functions. Let's get started. We start by introducing a notational tool that enables us to write piecewise defined functions in a concise, efficient way. This tool is called the Heaviside step function. Sometimes it's just called the Heaviside function, or sometimes just the step function. And in its simplest form, the Heaviside function has a value of 0 up until some critical t value. Here we have it labeled c. And then at t equals c, the function instantaneously jumps up to a value of 1. So here's the piecewise definition of a basic Heaviside function along with its graph. Notice on the graph, this t value here, where the jump occurs, would be t equals c according to this notation. As I mentioned here, there's a lot of different notations for this function, so just be aware that you'll see it written differently in a different class. Probably in every class it'll be written in a different way. Here, I will write it as u sub c of t. And this is the function that, quote, switches on at t equals c. C will be some specific value in a particular problem, as I've given in this, for example here. If the switch turns on at t equals 6, then I'll label that specific Heaviside function u sub 6 of t. And this wording that the function, quote, switches on at t equals c, I'll use that wording often. That's intuitively how I think of this function working. The function is turned off initially, so for t value starting at 0, the function is turned off, and then at t equals c, we flip the switch and the function gets turned on, in this case outputting a value of 1. So the Heaviside function can notationally be introduced into the expression of a function to accomplish sort of switching components on and off, as I've indicated here. If you have a component that you want to switch on at t equals, say, c1, you simply multiply that function, that component, by the corresponding Heaviside function. If you want to turn it off, if you want to switch off that function, then you multiply that function by negative u sub c2. So let's try this out. Let's try starting with a piecewise defined function. Remember, this is the type of function that will be the g of t in my differential equations soon. So let's start with a piecewise defined function, and let's sketch the function, then rewrite it in terms of appropriate Heaviside functions. In example 1, we do exactly that with two examples here. So let's start with a quick sketch of the g of t that's given here. This g of t starts out with a value of 0 for t values between 0 and 1. So I will just have a value of 0. The function just outputs down here on the t-axis in this case. And then at t equals 1, the function jumps up to equal 2. And it equals 2 from 1 to 3. Kind of pretend like that's a straight line. And then notice that the endpoints here at t equals 0, we do not include this part. We do include this part here. As it turns out, in the problems that we work with, that type of distinction is not typically significant, and so we don't have to get too bogged down in those details. But I'll try to represent it accurately here in these examples. At t equals 3, the function jumps back down to equal 0. I'll have another component here that's just along the t-axis. And then at t equals 4, and for all t values greater than or equal to 4, I've got basically this parabola. But notice that I've got a parabola. It's like I want to turn on a parabola. But in order to make sure it lines up here, I've shifted it over to the right 4 units so that it will apparently, in this case, continue kind of where I left off. That's not required, but that appears to be what this function is accomplishing. So I have just a standard parabola that continues off for larger t values, but it's been shifted over so that it starts right at that t equals 4 value. So this is what the function looks like. So now the question becomes, how do we write this function using appropriate Heaviside functions? And hopefully, as you see through these examples, this Heaviside representation is a little bit more concise than laying out all of these distinct cases. So first of all, my function equals 0. So I could write that g of t equals 0, but that's unnecessary. So I just won't write anything for that first component. At t equals 1, a switch turns on, and the output of the function is now 2. The way that I accomplish that is to introduce a Heaviside function that turns on at 1, t equals 1, and then I multiply that Heaviside function by whatever I want the function output to be. In this case, I want the function output to be 2. So I've multiplied 2 times that Heaviside step function. Notice that I need to turn that value off. So over here, when I hit t equals 3, I need to turn off that function. So we mentioned that the way we accomplish that is to simply subtract off that function multiplied by the appropriate Heaviside step function. So far, my g of t consists of nothing. The output is 0, and then at t equals 1, the output becomes 2. Notice at t equals 1, this component of the function hasn't turned on yet. So it's written in my function, but it hasn't been enacted yet. It's not until t equals 3 that gets turned on, and when I turn on this component, I effectively cancel out the first component. So that brings me back down here to 0. It's not until t equals 4 that I have something else happen, and so in this case I'll add, and I want the switch to turn on at t equals 4. So whatever the output of the function will be, I'll multiply by this step function. And starting at t equals 4, we said our output is going to be basically a parabola, an increasing parabola that has been shifted over. So I can just go ahead and multiply that function times the appropriate step function. So this g of t is a pretty concise representation that captures all of the different components and cases that are happening in this piecewise defined version in a more concise way. Let's try that again, part B. So let's once again start with a sketch. For t values between 0 and 1/2, the function is the function y equals t, or g of t equals t. So I'll just have a straight line coming out from the origin for that first 1/2 of a second. From 1/2 to 2, the function becomes t squared. Now we have to be careful because it's tempting to say I'm going to introduce a parabola that continues off at this point. But in contrast to part A, we haven't shifted this t squared at all. So really this t squared is like is in fact the parabola that starts at the origin and then continues up, but we don't actually turn it on. We don't get to see it until t equals 1/2. So I really should imagine a parabola that starts here at the origin, and for t values between 0 and 1/2, it's just invisible, essentially. And then at t equals 1/2, we will start to see that parabola, and it'll start to increase. And in fact, it'll increase well beyond the graph that I have indicated here, so that's a mistake on my part. But so I think it'll start something like this, and then it'll increase quadratically so that it, t equals 1, it equals 1. T equals 2, it's up at 4. And this is the part that I'm not going to be able to represent very well on my graph. Oh, that's a terrible parabola. You get the idea. So it continues up, and that should look like a parabola. I'm not doing a very good job. Hopefully your graph on your notes looks better. Notice at t equals 2, we do cut off that parabola. I'll sort of put an open circle there just to indicate that. So we do cut it off. And then from t equals 2 to t equals 3, we have sine. And once again, we haven't shifted it so that it starts in any sort of convenient way. We're just imagining the regular sine function just kind of rolling along. And then at t equals 2, we're just going to go ahead and pick it up. Prior to t equals 2, it's just invisible. And then we don't start using it until t equals 2. T equals 2 is a little less than, I guess it's a little greater than pi over 2. And so sine has its peak at pi over 2. And then we've got just this little segment. Let me just try to draw sine the best I can. This little segment of sine. That looks like a straight line, but you get the idea. That's the sine. It's kind of curvy. I'm not doing a great job with these graphs. That's my last component here. That's sine of t from t equals 2 to t equals 3. I guess it's colored in there. We do include that value. Here's an actual computer-generated graph. I wasn't too far off, but you get the idea. I'll just cover up my ugly graph here. So we have a sense of what the function looks like. Let's go ahead and represent that function using appropriate Heaviside step functions. Right off the bat, my function is equal to t. So I can just go ahead and introduce that. Sometimes you would write t times u sub 0 to reiterate that this function isn't defined prior to 0. But in most contexts, t values that we're considering are positive or non-negative. And so it suffices to just go ahead and include that t component there all by itself. But then notice that I do have to turn that t off at a time value of 1/2. So I will have to subtract off t times u sub 1/2 of t. At t equals 1/2, I'll turn on t squared, and then I'll turn it off at t equals 2. So kind of a common trick, and you can actually sort of see it structurally here. See how I could factor a t out of this? Sometimes we actually will write t squared, and then maybe in parentheses we would say we want to turn it on at 1/2, and then turn it off at 2. And so I can accomplish both switches, the switch on and the switch off, kind of here in the parentheses, and then those are multiplied by t squared. Sorry, I don't know why I put that 2 in the subscript. There we go. And then lastly, I've got sine of t, once again being turned on at t equals 2, and then switched off. And so I can kind of write it in this structure here and write sine of t times u sub 2 of t to switch that function on at t equals 2, and then minus u sub 3 of t to switch that function off. Sometimes these functions will be represented in this kind of factored form. Sometimes they'll be distributed out. So we have to be accustomed to seeing them in whatever form they show up. So here's two examples of taking a piecewise defined function and then representing it in a more concise way using Heaviside step functions. What I'd like to do next is quickly reiterate at the top of the next page this detail about shifting the function components as we saw in the previous example. In part A, as I pointed out, it was like we wanted to introduce the quadratic function t squared, but we didn't want to turn it on until t equals 4. And so we accomplished that by actually shifting the t squared function over 4 units and then turning it on. In contrast, in part B, none of our functions were shifted, and so they were sort of turning on and off in what kind of seems like a sort of awkward way. So this issue of shifting actually is a key detail that we really have to pay close attention to in these problems. So now that we've worked with the Heaviside function in a couple of examples, let's go ahead and compute the Laplace transform for such a function. And notice in the example here, I have explicitly incorporated that shift in the function that I'm going to take the transform of. So I'm not taking the transform of f of t itself. I'm actually taking the transform of the shifted version, so that the shift, in this case it's been moved c units to the right, matches the switch. And that's a key feature of this calculation and the result and how it gets applied in the context of differential equations. So as you'll see in subsequent examples, if I have a function that has been shifted 2 units, say, but I don't want to turn it on until t equals 4, that's kind of an issue. Like, I have to accommodate that. I have to manipulate the function as necessary so that the shift will match the switch. In this example, we're interested in computing the Laplace transform of such a shifted and switched function. So we'll go ahead and input this into our definition. And then just to clarify a little bit here, I've got a graph over here and I've sort of copied. So we originally have, like, this function is the function f. And we imagine the function f starting at t equals 0, but notice that I've taken that and I've shifted that over to start at t equals c. So when I think about this integral, the function is 0 up until t equals c. So I'm integrating starting at t equals 0, but nothing is happening until I get up to t equals c. So I could actually start my integral at c, and I won't be missing anything because my function is 0 prior to that. And in fact, once I've hit t equals c, then this switch has been turned on, and so it has accomplished its function, and so it's effectively now just acting as the number 1. So I could even, in this integral, drop this Heaviside function because it now is operating just as the number 1. So it's not contributing anything distinct to this integral. So here I've rewritten the integral without that Heaviside step function included. Next, I just noticed in this integral that there's sort of 2 independent variables in a way. It's as if t is the independent variable, but then it's also as if t minus c is acting as the independent variable. And so what I want to do is I actually want to make a substitution for t so that I can kind of rectify these two. In fact, what I want to do is I want to make a substitution so that t minus c is then sort of considered my primary variable. So I'll make this substitution here. I'm going to call the quantity t minus c, I want to rename that to be the variable u. That implies, if I just add c to both sides, that implies that t is that variable u plus c. And then dt is, of course, just du. So let me use this substitution to rewrite this integral. So here's the first expression that I get when I make that substitution. Actually, I guess I need to accommodate for these bounds as well. Notice that these bounds are t's, and if t equals c, then u will be 0. So I can write that this integral starts at 0, and of course as t grows without bound, u will also grow without bound. Let me rewrite what's going on in this exponent here. I've distributed the negative s through, and then I've got e to a sum, and so I can write that as the product of two exponentials. And now if you think about these quantities here, c is a constant. It's a fixed real value. And then s is treated in the context of this integral as a constant as well. So this entire exponential term is constant with respect to this integral. Since that's the case, I can move it outside of the integral. I also switched the order of the s and the c for no particular reason. And so looking at this expression, I've got this constant exponential. So this is interesting. This is the integral from 0 to infinity of f of something e to the negative s something d something. So this is actually the Laplace transform of f. It's in terms of the variable u instead of the variable t, which is what we're accustomed to. But this is the exact same integral. I just happen to have renamed that variable. And of course, the Laplace transform itself is a function of s. So what I happen to name the other variable is insignificant. So I could make the substitution. I guess what I'll do is I'll write that the overall final Laplace transform is going to be this exponential term in terms of s and in terms of the c value that corresponds to the switch that is involved in this particular function. And then let me just go ahead and write this as the transform, so I guess I'd call that capital F of s. So that is the Laplace transform of a function which involves a Heaviside step function. So let me just take a second to kind of summarize what this says. If we encounter a function of t that has this switch aspect to it, and for which the switch and the shift are aligned. In that case, what I do to find the transform is I simply find the transform of the original function f. Notice that this transform, in a sense, ignores the shift. I'm just finding the transform of f of t. But then to account for that switch, I will apparently see an exponential term in the transform, or I will be required to introduce that exponential term where the c in the exponential indicates the t value at which that switch occurs. So let's go ahead and try it out. So here in example 3, we're going to compute the Laplace transforms of functions that involve these Heaviside step switches. One thing I like to kind of do is just focus on the function itself that we're going to be transforming. So in this first case, in this first term, the function is the number 3, y equals 3 or g of t equals 3. So that's the function that I need to focus on transforming. The u sub 1 of t is of course just a switch that doesn't turn that function on until, in this case, t equals 1. Now, I stated when deriving the Laplace transform of such functions that we need to be careful to make sure that the switch matches the shift. So if this function is going to be turned on at t equals 1, the original function needs to be shifted over to start at t equals 1 as well. In this particular case, we kind of don't have to worry about that because my function is just constant. So if I shift that function left or right, it won't modify the structure of the function at all. So applying our previous result, when I transform 3, I get 3 over s. And then in order to accommodate this switch, I'll have to include e to the negative cs. C here is 1, so I'll just write that as e to the negative s. So that's not too bad. Similarly, on the second term, the function that I'm transforming is the function 3, or I guess negative 3. And then the switch here is u sub 2 of t. It's apparently we're turning on the value of 3 at 1 second, and then at 2 seconds we're turning that off. So applying the previous result as necessary, I get this transform here. And then lastly, I have the function t squared. Well, so actually I have t squared, but it has been shifted 2 units to the right. So here's a case of where I have to make sure this shift matches this switch, which it does. The structure of this is perfect. So according to my previous result, when I take the transform, I'm actually going to transform t cubed. So here's that theorem we just derived as a reminder, and notice the structure. It says that if you are transforming a function which is shifted, your output is the transform of the original function. So when I enact the transform, I don't have to worry about this shift. It'll be the same as if I was just transforming t cubed. So this is the transform I will get. And I will reiterate that this term is sort of perfect because the shift matches the switch perfectly. And as we'll see in later examples, when that's not true, we have to do some work to rewrite terms so that they get into this perfect structure. And then just real quick before I move on to the next example, I just want to point out that there are some algebraically equivalent ways of writing both my original lowercase g and my capital G, the original function in the transform. And I just point these out because we will run into these different forms in examples and web work problems, etc. And so it's just valuable to reiterate that, for example, this g of t was presented in a kind of the perfect way. Like I knew how to transform every term straight away. If you look over here, I've given two algebraically equivalent. I've just kind of modified the algebra. And so I've given two separate representations of the same function. Here, for example, we factor the 3 out of these first two terms. So then I have these two separate switches. This might be helpful because it clearly indicates when I turn this function on and off. Or if you'll notice in this second representation, I've sort of put the switches out front. And then here I have something happening at 1 second and then something happening at 2 seconds. So all of these are the same function, but I just point out that there's different ways to structure them algebraically. And so we have to be prepared to work with whatever form we're given and be able to maybe do a few steps of manipulation to get it into this kind of perfect form here so that identifying the transform will be as direct as possible. And then here I've written a couple equivalent forms of capital G just to also reiterate that this transform could be presented in any number of different forms algebraically. Anyways, let's move on to part B. So if I want to in part B, I can go ahead and start cranking out transforms. These first two terms don't have heaviside functions attached to them, so their transforms I can calculate directly. But before I get started on that, I just want to kind of look at these terms that do have heaviside switches. And I just want to reiterate, as I pointed out in the last example, when such a switch is present, we are forced to make sure that the associated function has the proper switch. In this t minus 2 cubed term on the previous example, all of that structure was set up perfectly for us. Down here, that's not true. So as I look at this term that has a u sub 1 of t, that means that before I can take the transform, I must modify this function so that it is in terms of t minus 1. And then similarly, on this second term here, I must modify this function before I transform it so that this t is in terms of t minus 1. And just to reiterate, that's because of the presence of this heaviside step function, which turns on at t equals 1. So when I have such a step function, the switch imposed by that step function must be matched by a corresponding shift in the function that's being transformed. So here's kind of what I mean. This e to the t needs to be written as e to the t minus 1. Well, I can't just modify that function. I can't just take e to the t and say, oh, now it's e to the t minus 1. So I have to accommodate that somehow. And here's what I'll do. I'll multiply by e to the 1. And then these two exponentials, when they're multiplied, I can add their exponents. And so this is equivalent to my original e to the t term. So it's a little strange, but I'm introducing this new coefficient here in order to force this exponential to have the structure that's necessary. Playing that same game with this second exponential, notice that this has got a 2 in front. So when I write it as 2 times t minus 1, there's actually an e to the negative 2 that I need to account for. And so I have accounted for that by introducing this e squared. And as I said, take a sec and multiply these two together, which would amount to adding these exponents. And I think you'll see, you can confirm that we'll end up with this original e to the 2t term that we started with. So this is what I've been talking about, how you have to make sort of modifications or something to accommodate the fact that the shift in the function must match the switch before you can apply the Laplace transform. So now I'll go ahead and take the transform. The transform of these first two terms will be straightforward. And then for these terms, I can apply the theorem that we derived recently. So this is the transform that I'll get. And just to remind us of the structure of taking the transform of one of these terms here, so I'm looking at this term here, this e to the 1 is just along for the ride, it's just a coefficient. And then even though this is e to the t minus 1, I take the transform of e to the t, which I've written here, and then to accommodate for this switch, I've introduced this e to the negative s. And then I do the same thing on this second term, and even though the function looks like it's kind of complicated, 2t minus 1 up here in the exponent, I'm really just transforming e to the 2t, and then I accommodate the switch here as well. And then here I've done just a little bit of algebraic simplification just to reiterate that we may be confronted or presented with this transform in the future, and we'll need to be able to sort of work backwards to be able to isolate, say, the shift components in these exponentials, the switch components in these exponentials, in order to be able to identify then the inverse, the original function. All right, let's continue with this example. We've got a couple more to look at.